Well, welcome back. We're going to do some more calculus. We're looking at the integration here and the basic formation of how we do integration with the power rule. So in derivatives, we have basic derivative power rule. And to kind of give you a little bit of background or a reminder of what that looked like, let's just say that we had f of x was equal to x to the fourth. All right, so let's say plus 5 on the end of this. So that f prime, or that derivative, would have been x to the third, but we've multiplied by 4 there, right? And since we're talking about derivatives being a rate of change, 5 doesn't change any, so it's plus 0 because it has no change attached to it. So 4x cubed is the rate of change of x to the fourth. Now what's interesting is if I were to find g of x to be x to the fourth plus 6, that would be g prime of x would be 4x to the third, which would be the same as f prime. Now that's useful to us here in just a second about what we're about to work with here. So because this is what this definition is here, and there's that plus c, right? That plus c comes from the fact that if we had a constant there, it doesn't matter what that constant is. I could define an h function here where we're doing plus some c constant value where we don't know, or it doesn't really matter what that value is. It's always going to give us this as its derivative, regardless of what that constant value is. So, example. All right, so if we have the integration of 3x to the fourth power plus 5x plus 6, and then dx, it's important that we put the dx on there because this is telling us which variable that we're working with. When we do that integration, we're doing the opposite process over here, which is why we're adding 1 to the exponent, and then we're dividing by the new exponent. When we were over here, what we did is we multiplied by the exponent, and then we subtracted 1 from the exponent. So now we're doing the exact opposite. So that becomes x to the fifth over 5. Don't forget the 3, because it was there already. And then here we have x to the second over 2. Don't forget the original coefficient. And then 6x, well, there's not an x there. So we got to remember that x to the 0 is understood to be there. So this is x to the first over 1, which doesn't really do anything, right? And then plus c, so this would be our integration of that piece. Now this particular one is what we call an indefinite integral because there's no values for a and b. The interval is not defined between particular spots from each other. Now that's different from what we call a definite interval. When we say definite, we're talking about we're going from a to b of some function here, dx, right? And the integration of little f would be big F. And that's just kind of a standard notation, as big F is a lot of times defined as being the parent function or the integration of f. And this would be f, big F of b minus big F of a. And this is the first fundamental theorem of calculus. Okay? You may be paying attention to the fact this is in chapter 5 and this is the first fundamental theorem of calculus. Well, the thing you got to remember is a lot of calculus is actually used and kind of created opposite of how we actually teach it and learn it in the United States. Is a lot of times we learn about limits first and then derivatives and integrations, but when we go back historically and look at how calculus was used, integrations were used long before we had a working definition of limits. So the first fundamental theorem of calculus is kind of like the beginning place of where we used a lot of this stuff. So here is an example when we talk about a definite integral. Let's just say the integration from 1 to 3 of x squared plus 2, all right, dx. Well, that's going to be x to the third power over 3 plus 2x, because it's x to the 0 under there, right there. So we add 1, which makes that an x to the first power, divided by 1, which doesn't change anything. Now, we're not going to put the c on there. We can. It doesn't change anything. But we're not going to because we have this definite integral piece. And according to this process right here with first fundamental theorem of calculus, is we stick in the 3, we stick in the 1, right? So 3 cubed over 3 plus 2 times 3, and then minus 1 cubed over 3 plus 2 times 1. All right. If we had the c on there, we'd have plus c here and minus c there, and they would cancel out, so they don't make any difference whatsoever on this process here. So now we have 3 to the third, which is 27, divided by 3, which is 9. So this is 9 plus 6. This is 1/3, and this is 2, right? So this gives us 15 minus 2 1/3, which gives us a grand total of 12 2/3 as our final value for that. So this is equal to 12 2/3. All right, so there's definite integrals, there's indefinite integrals. Process works more or less the same. It's just that when you have a definite integral, you have some extra steps after you've actually done the integration part of that. More videos to come on this, and if you need more examples, feel free to reach out. And then, of course, there are also lots of other processes that we need to work with when we come to doing derivatives. Take care.